In the previous videos, we learned that any instantaneous velocity of a rigid body can be represented as a twist, defined by a speed theta dot rotating about or translating along a screw axis s. In this video, we integrate the vector differential equation describing the motion of the frame twisting along a constant screw axis to find the displacement of the frame. This animation shows a screw axis s in a frame at time 0. Let's say that this configuration is coincident with the space frame S, so its representation is the identity matrix. Now we let the frame twist about the screw axis at a rotational speed theta dot equals 1. The animation shows the configuration achieved at times t equals pi and t equals 2 pi. These configurations are represented as transformation matrices, but an alternative representation would use 6 exponential coordinates, similar to the 3 exponential coordinates for rotation that we saw earlier. In this case, we could represent the configuration at time pi as s times pi, meaning the configuration achieved after the frame has followed the screw axis s for time pi. Similarly, we could represent the configuration at time 2 pi as s times 2 pi. Let's look at some of the analogies between rotations and full rigid body motions. For rotations, we have a unit rotation axis omega hat. For rigid body motions, we have a screw axis where either the angular component is a unit vector, or the angular component is 0 and the linear component is a unit vector. For rotations, the exponential coordinates are omega hat theta, where theta is the angle of rotation about the axis omega hat. For rigid body motions, the exponential coordinates are s theta. If the screw axis has any angular component, theta is the angle rotated about the screw axis. If the screw axis has 0 rotation, then theta is the linear distance traveled along the axis. For rotations, the matrix representation of the exponential coordinates is the 3×3 skew-symmetric representation of omega hat times theta. The set of all such matrices is called little SO3. For rigid body motions, the matrix representation of the exponential coordinates is a 4×4 matrix in little SE3, which we learned about in the last video. For rotations, the exponential maps matrices in little SO3 to rotation matrices, and the log maps rotation matrices to little SO3. For rigid body motions, the exponential maps matrices in little SE3 to transformation matrices, and the log maps transformation matrices to little SE3. As with the case for rotations, the matrix exponential for rigid body motions has closed-form solutions. There are 2 cases to consider. One where the screw axis is a pure translation with no rotation, and one where the screw axis has rotation. For the case of a purely translational screw axis, theta refers to the linear distance traveled, and the solution is particularly simple. The orientation is unchanged, hence the identity matrix in the top left submatrix, and the new position is just the unit linear velocity of the screw axis times the distance traveled. For the case of a screw axis with rotation, again a closed-form solution exists, but it is a bit more complicated. The algorithm for the matrix logarithm involves inverting these expressions to find the matrix representation of the exponential coordinates s times theta. Now, given a body frame B at the configuration TSB relative to the space frame S, we would like to know the final configuration TSB prime of the body frame if it travels a distance theta along the screw S. We could represent S in either the S frame or the B frame. If we define it in the B frame, the final configuration TSB prime is TSB times the matrix exponential. Remembering that multiplying by a transformation on the right corresponds to a transformation expressed in the frame of the second subscript. If we define the screw axis in the S frame, we must pre-multiply TSB by the matrix exponential, since multiplication on the left means that the transformation is expressed in the frame of the first subscript. Each single degree of freedom joint of a robot, such as a revolute joint, a prismatic joint, or a helical joint, has a joint axis defined by a screw axis. The matrix exponential and log will be used extensively in the study of robot kinematics, starting in Chapter 4. The next and final video of Chapter 3 covers the representation of forces and torques in 3-dimensional space.